Hello and welcome to the video. I'm Jari Honkanen. I write about FPGAs and VHDL at hardwaredescriptions.com, and in this video I would like to show how to create buses inside FPGA. Basically, how to create addressable, how to create addresses for registers. Now the basic idea, or the basic issue that we solve with this, with the bus, is that if we look at the code architecture here, now all of these boxes here are different modules, basically components with their own entities and ports. Now all of these lines here imply that the architecture is, the system is architectured so that first of all we have the top module, which instantiates a system control module, which then instantiates component interconnect, which furthermore has the power electronics and communications modules. Now if we look at our communication module here, it has an UART, and let's say that we have some register 1, that is in the system control module here, and we want to transmit it out through the UART. Now the first solution to this would be just to have access for the register 1 in the communications module directly. But this would imply that we would actually have to route it through 2 ports. First through the system control module to the component interconnect, and then from there to the communications module that then transmits it out with UART. Now this is very labor-intensive way of doing things, also that then implies that both of our component interconnect and communications module actually have to have some register that is defined in the system control in both of their ports. Now this is just even further obvious why this is an issue. That let's say that we want some other register 2 from power electronics module to be transmitted out of the UART, and we would also have to route it through the entire design. And in this case our communication module now depends on pretty much all of the parts of our design, and that is obviously not a good way to do things. Now what the bus achieves here is that the bus allows the communication module to, instead of accessing register directly, it allows it to read a value with its register or the register address. So let's say that instead of reading directly from system control a register that is routed through its port, it can have simply the bus at the communications module, in which case we can request a register from the bus, and when for example the system control module here then receives a command from the bus that some register needs to be written, it is then loading the bus value which is then caught by the system control module. So this actually achieves the dependency inversion, so that whoever consumes some data, whether or not it is reading or writing it, does not need to actually have the data, it just needs to have access to the bus. And whoever owns the actual register, let's say the system control module here, then that is where the read and write access from the bus is actually determined. So the system control module actually has access to its own register, and it only needs to know whether or not the register there is available to be read or written. And indeed, in this video we will be actually creating such a bus. Now we start out by simulating it. I have already created a test bench for the interconnect, and we will be actually adding directly the definitions of the bus into the package, because it'll be just way too much of a hassle to first create it in the test bench and then refactor it into the package. So we start out with creating a record for the interconnect, and this is going to be called FPGA interconnect record connect record. And what we have here is that we need to have the data, which is going to be actually STG logic vector. Now we are going to be using 16-bit data here, though since we can easily use VHDL 2008, that would allow us to actually leave these unbounded or undetermined size so that we can actually then dynamically use whatever bit width we would require. But just to make things simple, we're just going to use 16-bit for now. So the bus needs to have data and address, and also then it needs to have the read and write basically commands or bits which tell whether or not we are reading or writing data through the bus. So we have a read. First of all, write is requested with 0, and this is going to be an STG logic a signal of STG logic type, and we're going to be using 0 instead of 1 as the value which actually indicates that read or write is accessed, because we want to be adding these together to create a bus which has a pretty much multiple bus partners or masters and slaves connected together. So we need read and write. So we have read and write is requested with 0. Then of course we need a constant that is init FPGA interconnect and this is going to be of FPGA interconnect record type, and we will just have constant values for all of these. So we're gonna actually initialize the signal of this record type with our idle values, in which the bus is idling when it's not being driven by anyone. Now, next thing that we're gonna need, if we need to add this to the simulation, so we will have here use work dot FPGA interconnect package dot all. I'm manually compiling the package here for syntax checking. That's why I get the error whenever I do changes in the package here. So now this should be able to compile. No, we actually can't compile it because it is not found in here. So we actually need to add just the root and every VHD file from there. Now it should compile. Also, if you're not watching any of my previous videos, I'm using VUnit for running the simulations, and then I have GTKwave, which I will be using for looking at the waveforms. So we will start the GTKwave, and the VUnit, that's a VUnit out folder in which we have the test output, and from here we can find the wave.ghv, which is actually the waveform file for this simulation. Now, right now we don't have anything our FPGA interconnect aside from a simulation counter that runs from 0 to 50, or actually 49, because we are running this for 50 clock cycles as defined by this constant here. So first thing that we're going to do is we're going to add the first bus here. So this is going to be bus from stimulus, and that is because the main process that I have in this test bench is called stimulus. So this determines who is actually driving the bus. So we have bus from stimulus, which is of FPGA interconnect record type, and we will be initializing init FPGA interconnect. Init FPGA interconnect, like this. Now as we run the Python here, which actually launches the VUnit, which results in this command prompt that just says that everything is passed, which also loads now the, or we can actually load the newly updated waveform file into the GTKwave, but just Shift-Control-R shortcut. So now we can see that we have the bus from stimulus here, and we can actually add the addresses and datas here, so we can see that it is actually idling with all ones. We'll be using actually decimals here. So next thing that we need to do is we need to add the package body, and we are gonna start creating the functionality in our bus. Now the first thing that we need to do is we need to init the bus or setup. So this is going to be called the process procedure, which is called init FPGA interconnect, init bus, and this bus is going to be signal bus out and out directional, because we are assigning values to it, and this is FPGA interconnect record. Now what we're going to assign to this is just the init FPGA interconnect constant. Like this. Also I will be adding these long lines of dashes for visual guides here. And then we will publish this so that we can actually call it outside of this package, so it's visible by whoever actually uses this package. And right now we should be able to init the bus from stimulus, and this should now first of all ask me to compile all the header files, and then if I run the unit here, we should see no change. It just verifies that there are no issues with our code here. Now, the first thing that we need to, of course, do when we have a bus, we need to be able to write values with the bus. So we're going to create a procedure called write data to address. This has signal bus out and FPGA interconnect record. And in here, we will actually be putting bus out dot address. Actually, we need the address and data here. So address, which is an integer, and data, which is also integer. So bus out address is going to be written with the address, and at this point I will actually create a few helper functions here. So we will have a function called to std logic vector, which takes in an integer and returns an std logic vector. And this will have a variable. Actually, we was just going to do it directly. So return std logic vector to unsigned data and 16. These are primary expression needed. So here we have to STG logic vector and address, and then in here we have data, which is then set with data like this, and we are gonna run the bus out.write is requested with 0 to 0. Now the idea here is that we actually use the feature of VHDL, in which inside a process, when we have multiple drivers for single signal, the one that is written last takes priority. So when we init the bus, we are driving it with all ones, and then when we actually add a simulation counter case statement here, and when, let's say 5, we will write data to address, and the bus that we are using is bus from stimulus. The address that we are going to use is going to be 1, and then the data is going to be 35. I just randomly bashing our keyboard here. So when and others, and when other values are obtained, we will do nothing. Nothing. And also we need to compile our header files here. So as we actually run the Python, again we have verification that everything works as intended, and the GTKwave now shows that for 1 clock cycle our bus is being driven by 35, which is implied here, and the address is set to 1, and we are requesting a write when the write is 0. Now when we actually do something, indeed when we request a write, we of course need to be able to check that the write is requested. So we're going to add a function called write to address is requested. And this will be bus in, so FPGA interconnect record, and then address, which is integer. We don't need the input here. And this will return a Boolean value. So it will return true, return bus in dot write is requested with 0 equals 0, and we check that the bus in dot address equals, and actually we will be now doing other helpful function here, which is called function to integer, which takes in a STG logic vector, and it outputs an integer. And this is just gonna be the same as the STG logic vector, but in reverse. So we are gonna return to integer unsigned and data. So to STG logic vector equals, no, this is gonna be to integer plus that into the address is address. Now in VHDL, the single equals sign is just a relational operator, so this will return true when this is 0, when the data write is requested with 0 is 0, and simultaneously the address which is presented in the bus is address. And once again, we will be putting this function here so that it can be called by anyone who uses this package. And Then we actually also need a function which is just which will get the data, and this one has the bus, which is FPGA interconnect record, and it will return integer. And what will actually return is the integer and bus in the data. And also we will be declaring this so that it can be easily used, or actually at all. And now that we are gonna actually we don't have anything here yet, so what we're actually gonna create right now is another process. So process, this is gonna be endpoint 1, which is sensitive to simulator clock. And what it does here is that it checks that if write to address is requested from bus from stimulus, and the address that we are checking is 1, then we will actually get data bus from stimulus. And if now we do need to return some value, so we will actually add a signal data in endpoint 1, which is an integer, and we will be fetching the data in endpoint 1 when the write to address is requested. Now we'll actually check that this works, so that we will add a few others, so 35, 46 and 25, and then we will actually check that when we write some other address we are not getting anything. And we are going to run the Python again, and as we look at the values here we can see that the data in the bus gets 35, 46, 25, actually twice, and with the other time the address is in fact changed. And if we look at the data in endpoint 1 here, we can see that the value is 0 when it's initialized to 0, and then we are writing 35, 46 and 25 successively to the bus. So let's add something here, so 5895, and check again, just so that we can actually see that, verify that this is not actually getting in the data to from or data in endpoint 1. Now the next thing that we're going to actually need, now that we can write a data, is we need to read a data. So how this works is that we first of all need to check that the read is requested, and once the read is requested, then whoever has actually access to the register from where we want to read something, that then writes back the data through its own bus. So first of all we need the procedure called request data from address. This will get bus out and FPGA interconnect record. It's gonna be actually a signal. And then we need the address, so address, which is an integer. And the way it works is that bus out dot data read is requested with 0, is driven to 0, and the bus out dot address is driven with the STD logic vector and address. And the recipient needs to check that if data is requested from address, this is bus in FPGA interconnect record, and then address, which is an integer, and it will return a boolean. And the same thing applies here to what is here, with the exception that we are actually pass in the data read is requested with 0. Then we will actually go ahead and load both of these. So data is requested from address, and we actually request data from address. Like this. So now we can actually just check that if, actually we will then compile the header files here, and next thing that we will do is we will actually add a new one here and request data from address. We can now request 1. Primary expression expected here. No declaration for request data from address. Did we not just add it here? Request data from address. Return boolean. Right. So now this should work. So now we are requesting data from address, and if data is requested from address, pass from stimulus, and 1, which is the address here, then write data to address. Actually, we need a new bus here. So the way it works right now is that we first request the data, and then since endpoint 1 owns the register 1, it will then write data back through its own bus. So we need another bus here, which is called bus from endpoint 1. And we go here and we, of course, init internal bus from endpoint 1, and no declaration, it's called actually init bus, just without the internal part here, so init bus. And once it is initialized, we will actually write bus from endpoint 1 with the address. We're actually just going to use 0, and then the data in endpoint 1. We will actually also add another part here, which is called signal in stimulus, or data in stimulus, because this then allows us to check that if write to address is requested, and this is bus from endpoint 1. Actually, this is a typo here, so bus from stimulus. No, it is bus from endpoint 1. And we are gonna get bus from endpoint 1. And this is gonna be 0. Write to address is requested. So this is actually requesting a write to 0, so we are gonna read 0. Now this should actually work right now. So if we run the Python, we have several resources. Now that it actually fails, we can see that there are several sources for unresolved signal here. So bus from where is our did I just save? So we run it again. Here. So we are actually writing the data in endpoint 1 instead of data in stimulus. Now it works. So now that we look at this, we can see that the data is requested with 1 goes down. And if we now actually just take away all of these and just look at the data in stimulus, it is not being written. Because this is not actually, this should be bus from stimulus. So we were listening to the wrong bus there. Right, so now we can actually see that we can now get the register back from the endpoint 1 process here. And this is actually the major part of the functionality of a bus inside an FPGA. So if we actually had this spread out to multiple components, then these buses would just enter the component from its port. So we will actually now go ahead and add actually another bus called input 2. And this bus is going to be here just so that I can actually verify that we can write data to 2 different processes using the addresses. So now that we actually added another process, and we have once again a failure because of multiple drivers. So if we now look here, we should now see bus from endpoint 2 and the data from endpoint 2. And if we look at the data in endpoint 2, we can see that we're actually writing 5895, which is the odd register that we were writing here. Right. And then we can actually go ahead and request the data from the endpoint 2. So at this point we should be able to see the same data being transmitted back to the master or the stimulus process as soon as we actually just add these here. Right. Okay, so now we can actually see that the data in stimulus is actually being written by both the endpoint 1 and endpoint 2. Now, next thing that we can do is we're actually going to clean this up because this is a bit messy. Now the first part is we're going to actually combine the buses. So we will add a procedure, a process called combine buses, which is doing such that we add together the buses. So this is going to be a signal combined bus, signal combined bus, which is an FPGA interconnect record of init, and it's initialized with init FPGA interconnect. This, and then the combined bus will actually have added together all of these values here. So like this, and then we will go ahead and put here and then we will copy these again, put them here, and then pass from endpoint 1 and here we will have pass from endpoint 2 like this. Also this. Right, so now if we just actually change these both to combined bus and take this out, now we should actually see practically no change from what was happening prior, but now we are only looking at one bus back from the both processes. And also because I actually used a rising edge or clocked process for combining the buses, we actually have one extra clock cycle delay or latency between the reads and writes. However, since we used these functions that the bus itself tells when it is ready, the extra delay will actually not impair the functionality. It just adds one extra clock cycle of latency. Well, we could of course remove this and add them to the sensitivity list here. So if we actually wanted, we could do this. Pass from endpoint 1. And this should now have the exact same functionality as was before. Like this. But I actually prefer to have the one clock cycle delay here. Now, the next thing that we can actually do is we can overload an AND function and do this with the function. So this allows us to combine this instead of every term, then just using the two buses. So this is going to be left and right of FPGA interconnect record type, and this will return an FPGA interconnect record. And we will just copy these here. This is going to be left, and this will be right. And we will actually return this value. So return this. And now that we have this method to combine the buses, we can declare it here and just replace this with the ANDing function here, like this. Also, we need to compile our header files or packages, and then if we run the Python script, we can see that everything should be exactly as before with the extra one latency cycle added there. And we will actually refactor this a bit further. Now, we don't want to have all of this happening or being written every time we actually have a register added to the bus. So what we will do is we will create a procedure called connect data to address. This will have bus in FPGA interconnect record and then bus out FPGA interconnect record, and then we'll have the address, which is an integer, and finally we have signal data that is in, out, and integer. And what this actually does is that we will have all of these here with the differences that the bus from stimulus, so this is actually the bus in, this is also bus in, and bus in, and this is actually bus out, and this is going to be the data. Also data needs to be here. Parameter requires a signal expression. Okay, so this needs to be a signal. We will also add ins here, so it's not too confusing. So here we will indeed go ahead and add it to this list of declared routines that we use to manipulate, that we use the bus with. And now we should be able to actually just delete all of these and connect data to address with bus from stimulus, bus from endpoint 1, this was the register 1, and data in endpoint 1. And we also need to compile our header files or packages. Unit name expected. Oh, we need semicolon here. Also the same thing we are going to add here, and we just and here we will now compile, run the Python script out the test again, and actually we did not have address here, so address and address, and this one we run the VUnit script, and now we have the original implementation again. Also, we can in fact remove this and just add connect data to address and combined bus, and bus from stimulus address is 0 and data in stimulus. Right. And if we now go ahead and look at this, we should see everything to be the same. Right. So this is actually now our first revision with minimal implementation details of our internal bus here. And what this bus actually now does is that if we move the package here, it allows us to have just a very simple interface for communicating between different processes. So now we have ability to actually request and or read and write data from across different processes using just a common way of communicating. We'll actually add another function here, which is going to be just a procedure and connect read-only data to address, and this will have the bus in. Actually, it will have almost the exact same implementation as here, so we will just copy this. With the exception that the data is now of type in, and we will remove the write is requested here. So now we have actually both ability to connect data to addresses and also provide a secure connection so that we can actually read constants or signals that are not able to be written through the bus. So we can actually test this by adding a read-only register to this endpoint 2 here. So we will actually connect read-only data to address, and this is going to be 35,896 with address 3. And if we now go ahead and actually read and write to address 3, so this is going to be write to address and then use 3 and 0, and then we will actually request data from address 3. Now let's actually request data first. So 11, 12, and 13. So now what we do is we are actually gonna both read and write and request data from a read-only address, and what should happen is that we should only be able to see the constant data here. Data in stimulus has not been changed, and so despite the fact that we are actually writing the data here between the different read requests, we can see that the data in fact remains constant. So it is not being written to 0 in the interim. So next to that, what I'm going to do is I'm actually going to pause the video. You won't of course see it, but I will go ahead and route this bus to the project, which has the LED blinkers as was shown in the picture here earlier, and then we will actually go ahead and test the bus when it is implemented in an FPGA. So I will actually be back pretty much immediately. And now I have actually managed to write a little bit of a application here. So how this application works is that if we look at the original implementation here, so I routed the bus from the communication, which acts as the bus master initiating the reads and writes, and I routed through the component interconnect into the system control and power electronics. So if we go here, the way we have actually routed it is through the packages. So for example, in the system control, we have actually a register in system control which has a value 44252, and this is connected as read-only data to this address that is defined by this package here. So we have two addresses, 4096 and 8192 for the system control and power electronics addresses. And the system control, we have just we are initializing the bus, and we have one register connected to the bus here. And the way we actually have routed the bus is to have this package file which actually defines what these module ports actually contain, or the signals in the module ports contain. So since the system control module is instantiating the system components, or the component interconnect, then the component interconnect here actually has the buses in its input and output signal groups. And the component interconnect instantiates both the communications and the power electronics components. And it also has this same combined bus process, which actually just combines both the bus from system control and bus from the power electronics into one bus input that is then fed through the communications module. And in the communications module here, we actually have two functions. One is get address and one is get data. And this just allows us to get 16-bit data packets from UART, and the address will be the 4 highest bits in the 16-bit data package, and the data is the lowest 12 bits. And the way that this communications drives the communications module drives the bus inside the FPGA is that we have, when the 4 highest bits or the address is 0, we are going to write data to the power electronics address, and when it is 1, we are going to write data to the system control data address, and when it's actually 15, we will then write again the power electronics data address with the data that we obtained from the UART receiver. The UART is actually transmitted out at 100 kHz. I have 120 MHz core clock, so we have a counter that counts down from 1199, so 1200 ticks, and every 1200 ticks we actually, or clock cycles, we will be getting data from the bus. Actually, we can just get data. Get data from the bus. And we are continuously requesting data to be read from the bus with the address defined by the data that is obtained from UART. Now the power electronics address is written twice with all values that are sent with UART that are less than 4095, and every value that is larger than actually 61,440, so with all 4 highest bits of the 16-bit package as 1. And why we actually write 2 different addresses, or use 2 addresses to write the same, use 2 different data packets that are received from UART to write the same address, is that there are application functions such that when the write to address is requested from bus input that is driven by the communications module, if it's addressed to the power electronics module, then if the data is 1, in that case we will actually start the system, which is in this case just blinking some LEDs, and if it is 0, we will then actually stop the system or stop blinking LEDs. And in other cases, we will actually be connecting the data or writing the data to from this value here, which is the data from PowerXMix register. So it's a bit of a hacky application, but we can now write an address that is both that can be read and written, and then we can also write just this one actually system is started, or request the system to be started when we write there 1 and stop it when it is 0. So here is the Efinix Trion evaluation kit that I'm using, and if I just launch the UART, so this is my UART application here, and if we actually write a number 1 through the UART, we can see that the LEDs start blinking, and then if we write 0, the LEDs stop, and then we can actually, if we read the 4096 and lock the data, and once this is ready, we can actually get my Matlab here and plot the data here, and we can see that we are actually reading 44252 from UART, and which corresponds to actually this register in system control here. And then if we actually go ahead and take this again, and we write 80819692 actually, and we log the data, we should now be getting actually the state of the data from the PowerXMix, which was actually written as 1 when we started the system. So if I now go ahead and take the Matlab script here, we can see actually that there is 1. And the way we actually can write this register is that if we open this and we want to write, let's say, 16,589, let's actually do a large number, it needs to be less than 4096, so 3569. So if we write the register with 65,009, so we open this up and raw 65009, and then raw 8192, and log. And once this is ready, we should be then getting the value 65009 65009, and then log. And after that is ready, we will raw 8192, now log. And once it is ready, then we can actually see that the value that we wrote there is 653569. And also our LEDs are still blinking, if I can find here. And also if we wish to add a new register here, let's say to the system control, we could simply add another register, let's say 5589, and in this register we will actually have 35. And I can actually then open the Efinix software here and write the value to the register. Actually, we can't because we cannot really. Yeah, we actually can read. We can write, but we can read the register. So I will again stop here. Actually, pause here so that I can check that the register can be read. Right, and now that our code has compiled, we can now go ahead and raw 5589 here, and then log, and we should be then receiving the number 35 from the main system controller through the UART. And this should now conclude this video. Right, so we now get 35 from UART. So this now concludes the video, and just to recap or refresher here, what we actually managed to do in roughly an hour, it took me like 10 minutes longer than that to write application code, but in less than a few hours we actually managed to create a internal bus for the FPGA that allows us to read and write registers from different parts of the design with minimal effort, using these highly abstracted interfaces through the procedure and function calls, which also simplifies reading and understanding of the code. So, and I also just added probably one extra register here that can be now written from the bus. So, I hope you find this useful. Also, all of the code that I have seen here is actually can be found in the GitHub, which I will put link in the description for both the interconnect and the actual FPGA application here. So I hope you find this useful, and have a nice day.